In this video we will be looking at rotational kinetic energy. So we have traditional kinetic energy, what you might call linear kinetic energy, something moving left and right. We often call that translational motion. So that was 1/2 mv squared. You might be able to guess by now how these things translate into the rotational sense. I'll call this k rot for k rotational. The 1/2 is the same. Instead of mass, we have I for moment of inertia, and instead of v for velocity, we have omega for angular velocity. So kind of what you would have guessed here. We also have the work kinetic energies theorem, which still holds, and that told us that the work in the linear sense was force times the distance or displacement, and that gave us the change in kinetic energy. That holds true for the rotational sense as well, but instead of force we've got torque, instead of delta x we've got delta theta, and that will give us the change in the rotational kinetic energy. Now, rotational kinetic energy is just another type of energy, and it's part of the overall conservation of energy loss. So you can convert between rotational kinetic energy and linear kinetic energy, or some other type of potential energy, or you can dissipate it as thermal energy. So it just participates in the law of conservation of energy that we already know and love. So let's look at a quick example. If we've got a basketball rolling along on a horizontal surface at a certain speed, we want to find the total kinetic energy. So by total kinetic energy, we mean the sum of all types of kinetic energy, so the regular kinetic energy plus the rotational kinetic energy. By the way, I looked up these numbers, and these are accurate for the size of a standard NBA basketball. Anyway, we could find these separately and add them up, but I'm going to do it symbolically because things work out nicely that way. So again, 1/2 mv squared for this guy, plus 1/2 I omega squared for this guy. Now this equation is true in general for any rotating object that could also be moving linearly, so you just sum the two types of energy. But now we've got a ball here, basketball, and we are going to plug in I for a ball, and I for a ball is 2/5 mr squared. So I've got 1/2 times 2/5 mr squared. Okay, I've got my 1/2 mv squared still over here, and let's not forget to take care of this omega. Now for omega we can substitute in for that as well. So v equals r times omega, therefore omega equals v over r, and if I substitute in v over r and then I square it, that's going to be v squared over r squared. And you'll notice that these r's cancel out. So all I have left is an m and a v squared. So this guy I'll leave as 1/2 mv squared for now. I've got 1/2 times 2/5, which is going to give me 2/10 mv squared. And I just have to add these things. 1/2 is 5/10 plus 2/10 is 7/10. That's an ugly 10, but you get the idea. So here's a nice formula. This is only good for a rolling ball, so don't use this for a hoop or a cylinder or anything like that, just for a ball. But once we have this, all we got to do is plug in our mass. You'll notice that it's independent of the radius of the ball, so this here was extraneous information. We didn't even need it. So 7/10 times 0.625, multiply that by the velocity squared, 4.55 squared, and we get 9.06 joules of total kinetic energy between the regular translational or linear kinetic energy plus this new rotational kinetic energy. Now that we've got those ideas figured out, if you have something rolling down a hill, it's going to have both translational kinetic energy and rotational kinetic energy. So if you notice, when we do kinematics and even conservation of energy problems prior to studying rotation, we always have boxes sliding rather than balls sliding down a hill. And there was a reason for that, because the box does not have rotational energy, and so we didn't have to worry about it. If it does have rotational energy, that means it has less translational kinetic energy, so a sphere will actually roll down a hill slower than a box with no friction. Obviously, if there is friction, the box will be slowed down more than a sphere would be. But if we assume that this is a frictionless surface for the box will get down first. Here we have to have some friction. Don't you love how we do that? Pick and choose. Otherwise these objects wouldn't roll at all. They would just slide down just at the same rate as the box. But if we assume that these objects roll, and if this is a race and we let them all go at the same time, the sphere would get down first, and that's because it has the smallest moment of inertia. The moment of inertia of a sphere is 2/5 mr squared. Then a solid cylinder would be second. Its moment of inertia is 1/2 mr squared, which is slightly larger than 2/5. This is assuming equal masses and equal radii and all that stuff. An empty can, we don't really have a formula for that. Let's skip over that for a second. A hoop has a moment of inertia just of mr squared, so that's going to be the biggest. And we know that an empty can, if it's the same mass as the hoop, some of the mass on the ends is going to be closer to the axis of rotation than if all the mass were on the outer edge like the hoop were. So this is going to be a little bit smaller moment of inertia than this guy. But the solid cylinder has a whole bunch of mass in the middle, not just on the ends, so it's going to have a smaller moment of inertia. So anyway, that's how you can decide which one makes it down first. Now let's look at a rolling sphere a little more closely and do some analysis here now that we are considering rotation. If we want to find how fast this ball is going at the bottom of the ramp, saying that it started at the top here at height h, and we want to know the speed here at the end of the ramp, we'll do it with energy next, and that will be easier, but I'll show you the hard way first. The hard way, we can just analyze the forces acting on this, and without even considering rotation at all, we can write F equals ma equations, one for the x direction, here where we have our rotated axis, and one for the y direction. So in the x direction, we've got a component of gravity. It's going to be mg sine theta, minus friction, because that goes up the ramp, equals the mass of this sphere times a. In the y direction, basically the sum of the forces equals 0, and so the normal force is going to equal the vertical component of gravity. So we can say normal force equals mg cosine theta. Alright, then we can look at the torques acting on this sphere, and so we've got torque equals I alpha. Now there's only one force that's exerting a torque on this, because the ball is going to rotate about its center. The normal force will act up through the center, gravity will be pulling down from the center, so those aren't exerting, the lever arms are 0, those aren't exerting any torque. So the only torque we have is friction, so we're going to have friction times the distance, which is the radius of the sphere. I, as I mentioned earlier, is the moment of inertia of a sphere, which is 2/5 mr squared. And then alpha we can write as a over r, so that cancels one of the r's, that other r goes away, and we get that friction is equal to 2/5 times the mass of our sphere. Now if I go back and plug this in up into this guy, I'll just rewrite it over here. So I've got mg sine theta minus 2/5 m equals ma. Wait, I lost my a. I was like, hold on. Okay, so my a is still over here, which is good, because then I can combine these two terms. I can add 2/5 over here, so I get mg sine theta. So this is 1 plus 2/5, so 5/5 plus 2/5 is 7/5 ma. I can get rid of my masses, and then if I solve this for acceleration, I'm going to get 5/7 g sine theta. Now that wasn't the final question we were asking, but this is a useful bit of information. This is true for all spheres rolling down ramps if there is friction. You might remember a box sliding down a frictionless ramp, the acceleration is g sine theta, so the fact that it now needs to rotate will slow it down a little bit. And now we can do a kinematic equation to find the velocity at the end of the ramp. We can just use v squared equals v naught squared plus 2a delta x. because we have a constant acceleration, even though we have this other factor in there. It's still constant, so we can use our traditional kinematic equations. We're going to assume that it was released from rest. So we have the velocity at the bottom of the ramp is square root of 2a delta x, and then we can plug in the information we know. The acceleration we just found is 5/7 g sine theta. Now delta x, if we think about this ramp here, there's our theta. This is the opposite side, and delta x is the hypotenuse. So it works out that delta x is h over sine theta, which is nice because these sine thetas will cancel out, and then we just have the square root of 10/7 here times g times h, which once again is slower than it would be going if it just rolled down. Then this would be root 2gh would be the speed of a box rolling down a frictionless ramp. So this is a bit less than 2, so it's not going quite as fast. We can do this same calculation, finding the speed at the bottom of the ramp of a ball rolling down here with conservation of energy, and it works out a bit easier that way actually. So we've got our initial energy and our final energy being equal to each other. On this end, we've got gravitational energy. Our final energy is our regular kinetic energy plus our rotational kinetic energy. So we can start plugging things in here. This is going to be mgh. Linear kinetic energy is 1/2 mv squared. Rotational kinetic energy 1/2 I omega squared. This guy here, I was going to be 2/5 mr squared, and then omega squared, we can write that as v squared over r squared. So r's go away. We still have these terms here. mgh. Masses can cancel out. And so what are we left with? Well, we've got a gh here. We've got 1/2 v squared and 1/2 times 2/5 v squared. So that's going to be v squared times 1/2 plus 1/2 times 2/5. So we've got 1/2 plus 1/5. So that is what, 5/10 plus 2/10. So that's 7/10. Ugly 7. 7/10 v squared equals gh, and that works out to be the square root of 10/7, which is what we had before. Probably a little bit easier this way, doing it with energy. And this solution here is kind of a nice shortcut, so I would jot that down in your notes, as well as the one we solved for the acceleration of a ball rolling down a ramp on the previous slide, so make sure those get in your notes. Okay, see you next time.